Good morning everyone. My name is Sunil Kumar. I will be presenting my paper got accepted recently in SC21 conference. Title of my paper is Cuttlefish Library for Achieving Energy Efficiency in Multicore Parallel Programs. These are my co-authors. They are from IIIT Delhi and Berkeley Lab, USA. Nowadays, thousands of applications are running on supercomputer, weather prediction, complex modeling, several deep learning models also. The top left table shows some crucial statistic about top 3 supercomputers listed over top 500 website. Rank 1 supercomputer delivers 5 times more performance than rank 3 supercomputer, but it also consumes 4 times extra power than rank 3. And rank 1 have also twice the number of cores per processor than rank 3. It demonstrates supercomputer needs more power as well as more number of cores per processor to deliver better performance. Now we are moving towards the exascale supercomputer, which is expected to outperform all the existing supercomputers in terms of performance. It is also highly expected to consume more power than the rank 1 supercomputer, but the recommended power budget for these systems of 20 megawatt is lesser than power consumed by the today's rank 1 supercomputer. It is highly essential to make these systems energy efficient. Okay, there are several ways to limit the power consumption on multi-core processors. One of them is changing the processor's frequency. Multi-core processor has broadly two components, core and uncore. Core contains all the CPU cores available in your processor, and uncore contains on-chip memory. We call it cache also, which is faster than the main memory. Intel processor has designed their chips in such a way that these components can run on different frequencies at same time. There are two widely used techniques to change the processor frequency, DVFS for core component and UFS for uncore component. There are several approaches doing the same thing, but these approaches are application dependent or parallel programming language dependent. Also, they are not using both DVFS and UFS mechanisms simultaneously to save more energy. We proposed a runtime library, call it Cuttlefish, which is independent to parallel programming language and also applications nature. We tune both core and uncore frequencies simultaneously based on identified computational load on processor. So we identify the computational load dynamically in terms of memory accesses throughout the execution of application. So memory access means how many memory operations are performed in a certain time window. So in the motivational analysis, we plot a graph which shows variation in memory accesses throughout the execution. So here you can see last two benchmark UTS and SOR IIT has very low memory accesses throughout the execution, which shows it is compute bound benchmark, and rest of the applications shows very high memory accesses throughout the execution and also lots of variation in memory accesses. It means it is very high memory bound benchmark. In the fourth section, we made a table where we categorize memory accesses into two categories. High memory accesses means more memory operations are performed on processor. We call it memory bound region, where the CPU cycles are going to be waste. Therefore, the core frequency should be low in this case and uncore frequency should be high because we are performing memory operations. And the low memory accesses means less memory operations are performed, call it compute bound region, where the computations, lots of computations are happening on the processor. So CPU cycles are being highly utilized in this case. Therefore, the core frequency should be high and uncore frequency can be low because there are very low memory accesses are going to happen. After getting motivated from the insights, we built a Cuttlefish runtime library for multi-threaded application running over multi-core processor. We divided the whole execution of benchmark into several fixed time window. And this library has an analytical profiler which wakes up after every fixed time window and read memory accesses and total energy consumption was happened in the previous time window, and runs a very simple algorithm to find the optimal core and uncore frequencies. We made a tabular figure to explain the algorithm for one of the memory accesses encountered during the execution. In fact, there are lots of memory access you can encounter during the execution, and we have to perform the same algorithm to find the optimal core and uncore for all of the memory accesses. Every multi-core processor contains set of frequency levels at which they can operate. And this algorithm sets different frequency level for each time window. Linearly starts from the highest frequency. So the highest frequency in this case CF7, and got the total energy consumption 9.1, and then reduce the frequency level to CF5 and read the energy consumption, and keep on decreasing the frequency level until it gets the high energy consumption. And also it creates a log of energy consumption for different frequency levels, and then it finds the frequency level which consume least total energy and considered as a optimal frequency. So in this case you can say the CF3 is a optimal core frequency, and the same algorithm we will run for finding the optimal uncore frequency also. And here you can see UF5 consumes least power, you can say energy consumption. So the UF5 and CF3 is a optimal frequencies. And now we performed evaluation on 20 core Intel machine, and we got energy savings on each of the application shown by the green bar in the graph. And we normalize the results comes from the Cuttlefish with the Intel policy. So Intel also provided several inbuilt policies which makes your systems energy efficient, and we used one of them to compare the Cuttlefish policy, and what we got actually, Cuttlefish outperformed the Intel policy in each of the application. You can see here for memory bound benchmark energy savings we got 30%, and for compute bound benchmark it was around 10%. And there are some performance degradation also in memory bound benchmark, because in memory bound benchmark we tune both frequencies, core and uncore, and that's why we got some degradation also. And in future we would like to extend this policy on distributed memory parallel program. There are several applications cannot be scalable at single processor, so we need to use distributed architecture. We can't deploy the same library on distributed architecture also, because there are several other challenges could arise which needs to be taken. So we need to add more features to deploy this same library on distributed architecture. Also we want to extend it on heterogeneous architecture, which includes GPUs as well, and then we can think of deploying it on scalable computers like supercomputers. Thank you.